Okay, welcome everyone. My name is Ben Kropotski. I am the organizational director for the UNIFI Consortium, and welcome to our seminar series for spring 2022. Today, we have our speaker is Professor Xiaonan Liu from Temple University, who will be speaking about large-scale DER integration through scalable and secure secondary control in dynamic grids. And I'm going to go ahead and just let him get started on the presentation, and then we'll be taking questions afterwards. So thank you, Dr. Liu. Go ahead and start your presentation.
Sure. Thank you so much, Ben. And first of all, I would like to thank Ben and Dan for organizing everything. And more importantly, I really appreciate everyone being here to join my presentation today. Hopefully, we can have some more discussions after the presentation, and hopefully you enjoyed it. Okay, so my presentation today, the title is actually the large-scale DER integration through the scalable and secure secondary control in dynamic microgrids. Allow me to say that for my presentation today, I will mainly focus on the secondary control level. And I actually will focus on two applications. The first one is the dynamic microgrids, and also we have some extended work on the hybrid power plant as well, which will also highlight the applications of our secondary control level for coordinating multiple and large-scale grid forming inverters. So that is actually for the many of the work today. And maybe let me stop my video and let's focus on the presentation. Okay, so that's for the presentation. And first of all, allow me to maybe briefly introduce our group at Temple University. My group is named as APECS. The full name is the Advanced Power Electronics Group in the College of Engineering, Temple University. In APECS, we synergize power electronics, power systems, and advanced control knowledge for resiliency and sustainability enhancement in different types of energy systems. And we actually have three topic areas we would like to highlight. The first one is the APECS inverter, the second one is the APECS system, and the third one is the APECS control. For the APECS inverter, we actually would like to say that we focus on the next generation power electronics inverters, not only highlighting the main power circuits and control, but also considering the coordination among multiple inverters to see how we can effectively form the inverter clusters to support the external systems. And in the meantime, for the APECS system, the second topic area, we mainly focus on how we can use the grid interactive power electronics inverters at a system level, for example, mainly for the power electronics intensive power systems. And for the third areas of interest, we mainly focus on the APECS control area. And particularly, we would like to apply some control knowledge in power electronics inverter control and also power system control to, for example, to achieve different control goals, such as our stability analysis, like the small signal stability analysis of the overall system, and also the large signal stability analysis, for example, to identify the domain of attraction. So that is actually the major areas of interest in our APECS group. And we have, in terms of the personnel, so we have me, myself, Xiaonan Liu as the principal investigator in our group. And in the meantime, we also have our students, postdocs, and researchers in our group, whose names are listed here to recognize their contribution to our group. Okay. And first of all, let's maybe briefly touch some backgrounds. Actually, for the background part, allow me to use this very classic triangle to highlight power electronics. Definitely, the keyword here is power electronics, since we focus on our reforming power electronics inverter seminar, right? Actually, for the classic power electronics topics, we would like to highlight three aspects using this very classic power electronics triangle. We highlight the power area, electronic areas, and also the control area. And for our grid forming inverter control, it mainly focuses on how we can effectively control power electronics inverters. And we do have different types of applications. And particularly, I would say power electronics technologies are actually everywhere in different applications. The ubiquitous power electronics technologies in resilient and sustainable energy systems can be briefly summarized in this picture. As we can see that the major application, for example, is renewable energy integration, and also we can have the applications in motor drives, and also the applications in isolated power systems, such as the electric shipboards or electric aircrafts. And also also in the meantime, we also can highlight the energy efficient and great interactive buildings. And very importantly, we would like to highlight a major application of our work, which is the power grid. In terms of the modernized power grids and the applications of power electronics, allow me to use this picture to highlight actually different sections of power electronics and where we may apply our power electronics technologies. Particularly, the applications of power electronics can be penetrated into different sections, ranging from the bulk generation and the transmission sections to the distribution systems and even to the end users. Particularly for the generation system, we can have our hybrid power plants or solar farms or on the offshore wind farms and different types of applications in generation systems. And in the meantime, for the transmission system, we can actually also consider some different types of power electronics enabled devices, such as the fax devices, and also the combined HVDC and HVAC transmission systems. For the distribution system, that is actually majorly our focus. We can focus on the microgrid applications or the medium voltage DC distribution networks that are nested into the conventional AC distribution systems. And in the meantime, we can also consider the large electric vehicle charging stations, which can be also considered as the applications in distribution systems. And also for the end users, we can have the building integrated renewables and also some residential AC or DC nanogrids. There are some challenges. I believe my colleagues have already detailed everything in the previous presentations. So as a brief summary here, as we must know, the challenges in today's modernized power grids, we actually have the increasing penetration of renewables, the power electronics interface renewable energy resources, and they will give us the insufficient system inertia and the reduced system stability margin. And definitely we need to consider the complex operational dynamics between the power electronics interface resources and also the rotating generation units. And our solution is kind of a power electronics centric solution. And particularly we focus on the distributed energy access through power electronics inverters. And we do not focus on the individual inverters, but actually focus on the coordinated operation of inverter clusters. And in the meantime, we also consider the inverter enabled frequency and voltage support, which is kind of the main focus of our grid forming technologies in this UNIFI efforts. And actually, as we mentioned, my work mainly focused on the distribution section. So allow me to maybe highlight more about some more technical details in the distribution network. As we highlight as this very simple, the simple distribution network configuration, we can see different components in the system. For example, the renewables, or we can see the AC microgrids or DC microgrids. And in the meantime, some power electronics inverters interconnecting the AC bus and the DC bus, and also the inverters connecting the sources, different types of sources and loads. And actually, to better highlight the technologies we would like to introduce, focusing on the distribution section of the modern power grids, actually, we would like to highlight a couple of keywords. The first one is the central coordination versus distributed control. For the central coordination, we must know that for the distribution feeders, actually, we have the distribution management systems or DER management systems to coordinate different grid assets, for example, within each distribution feeder or across the different distribution feeders. And in the meantime, from the power electronics inverters perspective, we also need to consider the distributed control to make sure that actually we can achieve some distributed energy access and the corresponding control using individual and coordinated multiple power electronics inverters. In terms of the control of power electronics inverters, the keyword in our UNIFI consortium is the grid forming technology. And in the meantime, it is kind of the counterpart of the conventional technology named as the grid following control. For grid forming control, I believe it is actually the concept we understand at this point is actually to establish the frequency and voltage actively using our power electronics inverters, for example. And in the meantime, for the conventional grid following control, it could be a little bit passive since we actually need to follow the external grid voltage and actually inject active and reactive power in a controllable way. And also, I would like to highlight that for the work we highlighting here, no matter it is for the power electronics inverters themselves or the hosting system like our distribution system, we actually would like to understand them like cross-layer systems, considering both the communication networks and the distribution feeders or electric systems, electric networks. Basically, we need to have the electric network identified. That is actually something we need to control and to to control and also to implement some specific functions and where we need to implement some specific grid functions. And in the meantime, to implement everything, we actually also need to rely on some information exchange, no matter it is locally or globally. That is actually something we can implement through our communication network. So basically, we need to combine the communication network and our electric networks. So it is kind of the cross-layer cyber and physical configuration here. And in terms of the form of electricity, we need to consider both the AC side and the DC side to consider the dynamics in both the AC system and the DC system. That is actually not only something we may apply in our residential level, such as to our microgrids like AC or DC microgrids or nanogrids, but also to the medium voltage DC distribution system nested in the conventional AC distribution grids. And for sure, we highlight our power electronics generation units and the conventional rotating devices and grid assets should also be considered. That is where we may have some interactive dynamics and coordination needed for to see how we can manage both types of devices simultaneously. So that is actually our view and understanding about the applications of ubiquitous power electronics in distribution systems. And then let's maybe dive into the first topic area, which is actually about our dynamic microgrids with grid-forming inverters. As we mentioned, we mainly highlight our secondary control in the context of dynamic microgrids with grid-forming inverters. And first of all, it is some background and also some motivations we need to highlight. For the background, actually, we must understand the distribution system vulnerabilities, especially when we have some extreme operating conditions. We need to highlight that actually the distribution system and distribution network could be vulnerable. So there could be a large percentage of total outages that are induced by, for example, the severe weather events. And actually, we have to say this kind of power outages are not the same as the conventional power outages, since many customers may still remain without power afterwards. Actually, as briefly summarized in this table, actually we summarize some numbers of the power outage events examples. And as we can clearly see that the extreme weather events actually covers the most cover the most types of events that may trigger the severe power outages. In terms of the size and the numbers of customers affected, we can clearly see the impacts of this type of weather events and the corresponding power outages. And our motivation of this part of the work is to use dynamic microgrids with grid-forming inverters to actively mitigate the impacts of the power outages, and in other words, to enhance the resiliency of distribution systems. Okay, let's maybe start from some comparative understanding of the concepts. Actually, the concept of microgrids is never new. Actually, the concept of microgrids was even proposed when I was a student, like a junior PhD student. And actually, for the conventional static microgrids, we actually focus on kind of the static aggregation. Particularly, as we can briefly depict it in the picture here, we act for the conventional static microgrids. We focus on the static aggregation, as we mentioned, and as a result, actually, we have the static electric boundaries and static connection points with the external systems. And all the energy resources are actually managed in a static group, and the whole microgrid can be operated as a single entity. As we can see, actually the work, actually the dynamics and the operation flexibility we can leverage in the static microgrids are a little bit limited. By saying that, actually we may only disconnect some resources or disconnect the resynchronize the microgrids to the external system. So that is actually something we may leverage in terms of the flexibility, especially for the topology changes. However, what we would like to propose here is actually the dynamic microgrids. Particularly, we focus on the dynamic aggregation rather than the static aggregation in this work. And actually, with the picture depicted here, basically we try to implement the microgrids on the fly rather than fixing the topology of each particular microgrid into the static groups. And particularly, we can implement this microgrids with the breakers or some emerging on-off devices in the system to actually implement the dynamic boundary of each microgrid. So particularly, the topology of the system can be very flexible. We can have the dynamic electric boundaries and also the dynamic points of interconnection with external systems. And given that the system is implemented on the fly and very dynamic, actually we can have the energy resources grouped dynamically. And definitely the challenging part is how we can coordinate the distributed inverters, distributed resources with power electronics interfaces. And the coordination effort is something we need to consider in this overall framework. That is actually also one of our major efforts in this part of the work. This work is funded by the Solar Energy Technologies Office, US Department of Energy. Okay, we name it as actually Solar plus X solution. Particularly, we design this dynamic microgrids framework and name it and highlight the role of power electronics inverters, and particularly highlight the role of the solar energy resources. And as we can see from this picture, actually this is the very brief and just a sample distribution feeder configuration. And in this configuration, actually we have, as we can clearly see that we can have the power electronics inverter interface resources in the overall framework. For example, the PV panels, the batteries, or the wind turbines. And in the meantime, this is not only devices or resources or grid assets we may have in the distribution network. And in the meantime, we also have some conventional resources, such as the diesel generators or even the HVAC systems for temperature control. So these devices can all be considered as controllable grid assets that we may leverage to support the grid, to actually eventually support the resiliency enhancement in the distribution system. And our solution is actually a power electronics-centric solution to highlight the role of power electronics interface resources, such as the solar panels, and also consider how we can coordinate the resources here, the power electronics-based resources here, and also some additional resources, such as the conventional diesel generators and HVAC systems. And particularly, as we can see on this page, the pictures can depict that actually we can have the dynamic aggregation of different types of resources. And actually we can integrate the power electronics interface resources into different dynamic microgrids, different groups. And also, as we mentioned, the microgrids are actually implemented on the fly, meaning that actually the topology of each individual dynamic microgrids or the overall system topology can be very flexibly changed. And also during the whole framework with the flexible topology change, actually we need to consider that we have to guarantee system stability using our resources, which are actually our distributed power electronics inverters. We need to use them to actually ensure the system stability, no matter in the steady state or in the transit state. So that is the overall solution we are proposing here. And definitely for this overall framework, we can use it to enhance the resiliency and survivability of the overall system, especially the resiliency and survivability of the selected critical infrastructures. And this work is actually in collaboration with both this work is actually the collaborated efforts between the academia and also the industry. We have our collaborators of Argonne National Laboratories, Illinois Institute of Technologies, Southern Methodist Universities, and also we have our industry partners, United Technologies Resource Center. Now they are recent technologies. And also we get our advisory support from SNC company, mainly expertise in the smart switches or intelligent interrupters, and also some advisory support from our local utilities. And basically this is some bi-level solutions we would like to highlight. Particularly in the upper level, we see it as the optimization-oriented level. And particularly, we use the system-level optimization approaches to isolate the permanent faults, which is to basically determine the configuration of the system to see how we can implement the microgrids on the fly. And in the meantime, actually, we also consider the lower level, which is mainly the power electronics level, to identify how we can guarantee system large signal stability and small signal stability during this very flexible topology change in the context of a dynamic microgrids. And our work mainly focuses on the lower level at the power electronics level to make sure that we can ensure the control feasibility and also the stability of the system during this topology change with the dynamic microgrids. And also one very important point we would like to highlight is actually that the overall system is kind of a cross-layer system, meaning that we need to consider the main power circuits, the power electronics inverters, and also the distribution networks, which are all residing into the electrical power systems. And in the meantime, we will also need to consider the information exchange, especially in this part of the work, the localized information exchange. That is actually something residing in the communication networks. So basically, the interdependencies between the electrical power grids and the communication networks should be highlighted in this part of the work. And particularly for the approach we developed here, we leveraged the pinning consensus algorithm and implemented everything into the power electronics inverters, the distributed control framework. And actually for this part of the work, we specifically designed this approach and use it since actually it is very flexible for us to designate the pinning power electronics inverters and also the following power electronics inverters. Here, our reforming technologies are mainly used in our pinning power electronics inverters. And it is worth mentioning that actually we can very freely change the role of each bus and actually to designate different buses as different inverters as the pinning bus based on the actual real-time availability of each distributed resource. And in the meantime, for the following nodes or following power electronics inverters, they mainly participate in injecting the controllable active and reactive power into the bus, into the point of interconnection. That is actually the following buses we identified in this collaborative framework. It is also worth mentioning that the motivation and the reason for us to select this pinning consensus algorithm is actually that we can also consider the dynamic aggregation of power electronics inverters, which can be easily incorporated into this framework without violating the set points or the design algorithm in the pinning consensus framework. And it is actually very easy for us to implement a smooth mode transition between the pinning nodes and the following nodes, and also the dynamic aggregation. The aggregation is easy to implement. And based on that, we would like to also dive into some more and further technical details here. Let's maybe take a look about the left figure first. As we can highlight it here, we mainly focus on the secondary control level in this overall framework. As we mentioned at the beginning of this work, it is actually our vision and idea that actually the inverters shouldn't be only something related to the main power circuits or something about the main power circuits and the controls. Actually, we also need to consider the cross-layer dynamics and interactions, including the interactions between the main power circuits as well as the control diagrams and also the local communication networks. Because, for example, for this part of the work, we rely on distributed control, and it means that we at least need to understand for each inverter, it at least needs to understand what is happening at its neighbors. So basically, we need to rely on some neighboring communication networks to make sure that we can get information from some neighboring power electronics inverters to facilitate the control. It is something like a gossip theory. Actually, we can talk to our neighbor, and our neighbor will talk to their neighbor as well. So eventually, we spread the word, and actually, we cover the full picture of the entire system. That is actually basically how we can satisfy the scalability requirements in this proposed work. So basically, from the inverter perspective, we name it as a resilient inverter control. And also we highlight and put special emphasis on the cross-layer, cross-main power circuit, and also the communication network dynamics in this particular example, and I mean inverter control example. And in the meantime, the concept is not only for the inverter itself, not only for the individual inverter itself, it is actually also something applied to the overall system. As we can see that, and also as we introduced briefly in the previous slides, actually the system is implemented following the very frequent topology change. Basically, we implement the dynamic microgrids on the fly. And it actually means that we need to consider, the frequent topology change of the system, considering the aggregation of the different resources, inverter-based resources with the reforming control, for example. However, we also need to consider that in the communication network, we still have the same nodes, the same resources, but the communication network topology could be different. In other words, we may have different topologies in the physical network and also the cyber network. That is actually totally fine for this approach, as long as we can ensure the availability of the information of the system and the controllability of the system. Therefore, actually, two keywords we would like to highlight here in the overall system reconfiguration for the formation of dynamic microgrids are the independency versus the interdependencies. So basically, we can independently implement the dynamic microgrids on the fly in both the communication network and also the physical network. And in the meantime, we still respect the interactions between the layers to make sure that the information exchange and the controllability can be feasible. So that is actually some further details we would like to introduce for this dynamic microgrid solution with solar plus X and also grid forming technologies. And also to make this thing actually happen rather than only the paper design, we need to make some actual definitions and the implementation first. The first one is actually to make it more practical, is actually to make sure that we can implement some minimal building block. It's actually like Lego. We actually always would like to find the minimal piece that is probably the most useful in all the configurations of Lego buildings. Actually here, for this one, we are also identifying some minimal microgrids as the building block of the dynamic microgrids. Particularly for the minimal microgrids, we consider, first of all, two things. The first one is the local energy resources, for example, inverter-based resources like solar panels, wind turbines, or energy storage units. And in the meantime, also very importantly, we need to consider the critical infrastructures and the critical loads in the minimal microgrids, because the motivation of our work is for the resiliency enhancement, especially for the resiliency and the survivability enhancement of the critical infrastructures and we actually can implement the dynamic microgrids on the fly, considering the availability of the power availability of the resources to actually implement the individual dynamic microgrids surrounding the critical infrastructures. So that is actually the minimal microgrids we define here. And for sure, the minimal microgrids are designed to ensure the self-sustainability, even in the autonomous and islanded operation. And actually, one more important thing we would like to highlight is actually about the switches between the neighboring minimal microgrids. Actually, this is a switching framework, and we need to rely on some breakers or smart switches to implement this switching network. And actually here we name one breaker as one example. That is the smart switch. Actually, it is not fully hypothetical devices, and in the real applications, actually, we do have some intelligent interrupters which can provide some similar functions. So that is one example breaker we may use. And in the meantime, we can also implement dynamic microgrids in coordination with the conventional breakers. That is some additional extended applications of dynamic microgrids. So basically, this is the building block of dynamic microgrids, and the actual dynamic microgrids are actually implemented by merging some neighboring minimal microgrids. And in the meantime, we may also split each dynamic microgrid into some smaller pieces, but definitely our minimal microgrid is actually one of the smallest pieces in the overall framework. So that is the building block. And in terms of the communication requirements, as we mentioned, we do need to implement the distributed control residing in the power electronics inverters, considering some local communication networks. And to make the things actually happen, we actually consider three types of communication networks. The first one is about the resource-to-resource communication network. For each resource, we refer to the grid-forming inverters in the overall dynamic microgrids framework. And actually, we need to consider the communication network built between or among the inverter-based resources within each minimal microgrid. And in the meantime, also, some smart switches can participate in the communication network. If so, we can also enable the local communication network between the smart switches and local power electronics inverters like the solar inverters or battery inverters. And in the meantime, actually, we also consider the switch-to-switch communication network if that is available. And if so, we can also enable the communication between the breaker-to-breaker communication for information exchange that may bridge the information exchange among multiple minimal microgrids. So that is actually for the communication requirements as we introduce here. Okay, here are the control diagrams we developed in this overall framework. Definitely, I do not want to dive into all the mathematical details on this page and the following page, but if you have interest, you can always look into our published papers to summarize all the details here. However, I still would like to introduce some different categories of control functions we implemented in this overall framework. The first one is actually the first thing we would like to highlight is actually we implement the overall framework based on the primary control, and particularly we select droop control as the fundamental grid forming control function we implemented here. And our work and the additional control efforts are incorporated into the secondary control level, represented using a couple of compensation terms as we summarized here. And for the compensation terms, they are designed to satisfy different control needs. For example, some of the control needs are related to the steady state operating performance, such as the frequency restoration and the voltage magnitude restoration, and also the accurate active and reactive power control and sharing. And in the meantime, actually, we also need to consider the transient states, which are actually very important in this dynamic microgrids framework, since we implement everything on the fly. Particularly, we need to consider the power sharing across the minimal microgrids, which can be very dynamic since we may change the topology of the system and considering different configurations and consider different configurations of how we merge and split the microgrids. And in the meantime, since we need to turn on since we need to open the breakers and also close the breakers, we also need to consider the through power, the through active power and reactive power. For example, for the cases when we need to open the switch, actually we need to minimize the through active and reactive power first so that we can very safely open it. And on the other side, when we need to close the switch, the resynchronization efforts are also considered and incorporated into the secondary control level as one of the compensation terms we incorporated here. That is actually something we developed for the positive sequence control diagram. And for the negative sequence control diagram, we actually also considered that. This is actually the motivation of the negative sequence control diagram is actually first, our US distribution network is mainly the unbalanced distribution network. That means actually focusing on incorporating dynamic microgrids into the unbalanced distribution network, we do need to consider the unbalance, which can be managed using our negative sequence control. And actually also for some additional functions, they can be incorporated into the overall framework. And actually one of the additional functions is actually the voltage unbalance mitigation at critical infrastructures or at critical buses. So that is actually something we can incorporate it here. To minimize the voltage imbalance, actually we need to consider some negative sequence control to use some negative current regulation and also leverage some virtual conductance built based on the negative sequence model to mitigate the imbalance. So that is actually for the negative sequence control functions we designed in the overall control diagram. Okay, so this is actually the overall picture. As we mentioned, we first of all consider different types of operation modes, and we define different mode selection. And in the meantime, we design the positive sequence and the negative sequence control functions. And all the control functions are modeled as the conversation terms incorporated in the secondary control level and eventually added to the primary control level. And we focus on the scalable and distributed secondary control in this overall framework in the context of dynamic microgrids with grid-forming inverters. Okay, in terms of the testing, since this is actually not only for the individual inverters, we actually focus on the cluster of inverters to highlight the coordination. And so here, actually, we use the standardized IEEE distribution feeder, and we use the IEEE 34 bus test feeder as an example, highlighting the imbalance in the test system. And in the meantime, we have the dynamic aggregation of the grid-forming power electronics inverters, and also to implement dynamic microgrids on the fly. And definitely, we highlight the interactions between the communication network for information exchange, and also the physical network for power sharing and the frequency voltage regulation in the multi-inverter systems. And the testing is actually also in collaboration with the North Carolina State University. And for the topology change, we particularly actually select the test system with actually 5 distributed energy resources with the power electronics inverters. And we actually consider 3 smart switches in the system. So basically, actually, we have 4 minimal microgrids, the 4 building blocks in the system. And in the meantime, for the different topology change scenarios, it can be highlighted on this page as well. For topology number 1, actually, we consider 2 microgrids in the system. And for topology number 2, the original 2 microgrids have been merged together to form one single microgrid. And for the topology scenario number 3, the original single microgrid is actually split. The original single microgrid actually splits into 2 new microgrids. So our work is actually to guarantee that the control performance is acceptable for the overall process. As we can see here, actually for the frequency and voltage waveforms, as we can see, if we do not apply any proposed control, actually we can see the significant transients, for example, in frequency and also in voltage. They may trigger some very significant instabilities in the system or trigger the actions of protective devices, which may even fail the entire system, which is definitely something we do not want to see. And when we apply our proposal control and activate our proposal control functions in both the positive and negative sequence, as we can see in the black curve, actually the significant transients can be mitigated. And more importantly, for some additional functions, for example, the voltage imbalance factor mitigation at the critical buses, actually they can also be controlled to a lower level. Accordingly, the active and reactive power contribution, no matter the positive sequence or negative sequence, can be depicted on the middle side as well. And just to highlight the transients, some sample results can be also shown here. For example, when we about to close the switch, actually we need to activate a corresponding compensation term in the system to synchronize the system. I mean, basically to synchronize the voltage across the switches using our power electronics inverters. And after the synchronization, actually the difference between the 2 waveforms can be significantly minimized. So that is actually the way for us to mitigate the impacts during the transients. Okay, another topic we would like to talk about today is actually about the secondary control in hybrid power plants. And in the meantime, we also highlight the secondary control we developed in this particular application to see how we can integrate and design the control function for a cluster of grid-forming inverters. Particularly for the hybrid power plants, this is actually not only in the distribution system, but also in the generation or transmission systems. And particularly for the hybrid power plants, we can actually use them to integrate the inverter-based resources such as the PV panels, wind turbines, or battery banks. And actually, the whole hybrid power plant can be used and seen as a controllable node to the external grid at the point of a common coupling. And definitely, the HPP, the hybrid power plant, can provide the auxiliary services to the external grid. There are also some challenges we need to highlight. I believe many of my colleagues have already introduced the details about the challenges in the previous presentations. So basically, as a quick summary, actually the conventional generations units have a very large mechanical inertia. However, from our inverter-based resources in the hybrid power plants, actually we do not have the benefits from the large mechanical inertia from rotating generation units. So we actually have the power electronics dominated system, the HPP. So the stability is actually a concern. Particularly, the challenges may be summarized in this brief flowchart in different categories. Particularly at the asset level, we highlight the inverter interface, the PV panels, and also the batteries. And the challenges fall into different categories. Actually, we may have the multi-timescale dynamics, and in the meantime, also the mixed AC and DC side transients. And more importantly, we may have different types of control loops in the overall HPP to be considered together, and we need to coordinate them for sure. For example, we may have the conventional droop control or the conventional, multi-loop control. And in the meantime, we may have some additional control loops such as the virtual impedance or some secondary controllers we need to design. So the coordination is the key. And also for the HPP level modeling, we also need to consider the system configuration as well as the plant level control, the HPP level control. Particularly, we may say the HPP is actually a little bit similar to the conventional microgrid, but it is actually not exactly the same. They are not exactly the same. The reason for that is actually we may have, for example, some intermediate DC bus to couple the DC-DC converter stages of the PV inverters and also the batteries. And in the meantime, we may have multiple parallel DC to AC inverters to interface the DC bus and the AC bus. So the configurations could be not exactly the same. And in the meantime, generally, we would like to have the HPP to be treated as a single entity with, for example, grid-forming controls or grid-following controls. I believe the preferable way is actually to run the HPP in a grid-forming as a grid-forming unit. And also in terms of the stability analysis, actually we need to highlight the large signal stability analysis versus the small signal stability analysis. It is actually necessary for us to quantify the stability margin. For example, for large signal stability analysis, based on our research, we noticed that definitely 100% grid-forming is definitely beneficial. But actually for small signal stability analysis, it could be a different, the minimal percentage requirements of grid-forming inverters that may give us the best scenario in terms of a system small signal stability enhancement. So that is something we may need to look into to clarify. Okay, this is actually some brief introduction about grid-forming versus grid-following control, and actually to highlight different types of buses we may build using different types of control functions. And I believe it benefits, the pros and cons of grid-forming, grid-following or have already been detailed in the previous presentations. So I think probably I do not need to dive into all the details here. But what I would like to say in my presentation is actually, for example, moving from the very conventional grid-following inverter control to the grid-forming control with only the frequency and voltage established, and also to the grid-forming inverter control, such as with droop control, with some coordination among local units. Actually, we have this process to see how the technology can evolve. And in the meantime, actually for each type of a control function, we may end up build different types of node using different control functions here. This part of the work can be actually detailed in this particular example. I would like to say, what is actually the current status? That's something I always would like to revisit to see how things is developing currently. Actually, we have quite a lot of grid-following inverters as conventional units in today's power grids. And in the meantime, we are actually actively working on deploying some grid-forming inverters in the grid, which is definitely beneficial. And actually, the current status is no matter what, it could be very possible that we have a mixed combination of grid-forming and grid-following inverters in today's power grids. And actually, that is something we may need to consider. As we mentioned, based on our existing work, we are definitely keeping working on that. Based on the work we currently have, we noticed that for large signal stability enhancement, 100% reforming in water is actually very beneficial to ensure system large signal stability. But the system stability evaluation actually covers both the large signal stability part and also the small signal stability aspect. So basically, in terms of the small signal stability enhancement, actually the minimal percentage requirements of reforming in water that may give us the largest small signal stability margin could be different. So that is actually the motivation of our work for developing the secondary control, targeting the hybrid power plant applications. Particularly, we would like to leverage the grid forming and grid following mode transition as an actual degree of controllability. And back to the control diagram, actually, we would like to develop a couple of modular control functions in the secondary control level to coordinate multiple units within the hybrid power plant. And particularly for each power plant, for each HPP, it can be seen as a PQ, it can be run as a PQ bus or PV bus or V delta bus by activating different modules in the secondary control level. Here are some more details. Basically, it is actually a bi-level hierarchical control diagram designed for different applications, different operation modes. We still use drip control as the fundamental control function in the primary control level. And in the upper level, we name it as level 2, localized coordination. At the plant level, we actually can flexibly designate the operation modes of each particular HPP and to designate it particularly as a PQ bus, PV bus, or V delta bus. Particularly for level 1 algorithms, we actually designed this very conventional drip control as the function we may use here. And in level 2, actually we design different modules as we can detail here. And to activate, and by activating different combinations of the modular control functions we have in the secondary control level, we can actually control the HPP as different types of buses as we can control in the overall picture. Again, actually, allow me to highlight, actually, this part of the work is mainly to enhance the system's small signal stability. So to do that, definitely the first step is actually to derive the holistic small signal model of the entire system. Here, we generally focus on a modular configuration to derive this small signal model of the overall system. And particularly, we focus on the conventional power plant represented using the synchronous generators, and also the hybrid power plants being represented using the parallel inverters. And also, the loads and the networks are also modeled to derive the corresponding small signal diagrams and also models. And then the A matrix is something we need to highlight based on some power system analysis approaches. And then we actually can define the system's small signal stability margin, which is defined as the maximum real part of the non-zero eigenvalues. And actually, as we must know, for this omega m, if it is smaller than 0, the system is stable, small signal stable. And if it is, we actually need to make it sufficiently small to ensure system small signal stability. Particularly, we also can conduct some model analysis to identify the effectiveness of this approach and the potential impacts of this approach as the developed secondary control in hybrid power plants with reforming control functions. And for the model analysis, as a very brief introduction, actually we may have different modes identified based on the responses we triggered in the system. And actually we can highlight the damping ratio and also the oscillatory frequencies in the model analysis. And it could be noticed, it could be highlighted that we may want to put special emphasis on the oscillatory mode with a low damping ratio and a low damping frequency, since it may trigger some potential stabilities easily in the system. Particularly, this is the system we identified as a test network to see, to conduct a model analysis and also conduct some corresponding following case studies. And particularly, we have one synchronous generator considered, and actually 4 HPPs considered with the power electronics grid forming inverters. And with that, with all this considered, actually we can conduct a model analysis to identify the impacts of operation mode transition. Remember the PQ and the PV operation mode transition on system and dynamic performance. Particularly based on the analysis results, as we can see the data in these tables. In the first table, actually that is the oscillatory mode, the model analysis when we set all the 3 HPPs in the PQ operation mode. And then we actually change HPP number 3 from PQ mode to PV mode. And then in the third table, we actually change the operation mode of HPP number 2 and HPP number 3 from PQ mode to, both of them from PQ mode to PV mode. So as we can see that actually with the operation mode transition, we can identify some unchanged oscillatory modes, which actually represent the intrinsic oscillatory characteristics, particularly representing the couplings between different units, for example, coupled through the main power circuits, the power network. And in the meantime, we also identify that there's when we trigger some oscillatory mode, when we trigger some operation mode transition, we can also see that some of the oscillatory modes may have the increased damping ratio, which is definitely beneficial for us to dampen the small signal instabilities in the system. And in the meantime, we also need to highlight that there might be some additional operation modes triggered as well. That is actually something we need to avoid in coordinating the selected operation modes and the overall HPP. Particularly, there are some additional case studies we would like to highlight. And in this particular system, we actually can see that for the small signal stability analysis, with the change with varying penetration levels, when we have smaller than 70% penetration level, the system is actually stable with a lower than 0 stability margin. And actually, unfortunately, for the original system, when we set all the HPPs in the PQ mode, and here as a side note, for the synchronous generator, we set it as a V delta mode. And actually, if we set all the 3 HPPs all in the PQ mode, the system will be small signal unstable with larger than 70% penetration level of HPPs, the inverter-based resources. And then when we enable our operation mode transition in the design secondary control level, actually we can see that for the entire system, even with 100% penetration level, the system stability margin can be maintained below 0, meaning that the system stability, small signal stability can be guaranteed even with very high penetration level. Here we actually also listed the selected operation mode for each HPP. Let's maybe take a deep dive into some additional cases here. Actually, if we fix the output power of the 3 HPPs to 0.2 per unit, 0.5 per unit, and 0.2 per unit respectively, actually we can identify the combination of the different modes in the system. And with each combination of the operation modes, we actually can calculate and derive the corresponding stability margin. As we can see that it is actually true that we may have some stable cases in the system, given that we are changing the control diagram of the system. And actually for some other cases, unfortunately, there are small signal unstable cases. So what we can choose is actually the one that can give us the stable system for sure, small signal stable system for sure. And particularly we can choose, in this particular example, we can choose the combination number 6, since the stability margin is the largest. In terms of largest, I mean the stability margin is actually the smallest. Here are some brief testing results as we can show the stable cases and unstable cases. When we select operation mode selection combination number 6, as we show on the previous page, the system is stable. When we trigger, for example, the frequency, as we can see in the frequency, when we trigger some load changes, the system is stable. And in the meantime, when we have the operation mode selection, the combination number 3, that indicates an unstable, small signal unstable case. And when we trigger the small load change in the system, actually the frequency will become an unstable one. Okay, here are some quick summary. We actually highlight secondary control in different applications, but definitely with a special emphasis on grid forming inverters. The first one is the application of a secondary control in dynamic microgrids. Actually, we designed the secondary control level with different compensation terms to make sure that the dynamic microgrids with grid forming inverters can be implemented to freely change the topology with stability guarantees. And there are actually a couple of enabling devices and technologies we need to highlight, such as for sure, the inverters, distributed control and the distributed inverters like PV inverters, battery inverters, and also the building block minimum microgrids. And also there are some additional functionalities we can incorporate into this framework. And for sure, we need to respect the cross layers, the cross cyber physical layer dynamics in the overall system. And the second part of the application of our proposed work is actually about the applications of hybrid power plants with grid forming inverters. And we developed a set of inverters to enable different types of operation modes and also the smooth transition of different operation modes in the overall system. And particularly, allow me to highlight, we focus on the small signal stability enhancement in this overall framework. And we can do the model analysis or additional analysis to actually verify that the operation mode transition can actively enhance system small signal stability as an additional layer of controllability. Okay, some quick future trends. I would say to also echo the keyword of secure. Actually, for secondary control, no matter what, we need to rely on some information exchange. So that means we may disclose ourselves at least to our neighbors, but we may not want to. That is actually the balance between the privacy preserving and also the information exchange. And in the meantime, we do not want to run into the computational stress. Actually, we also need to think about the balance between the information security and also computational efficiency. We do have some preliminary work which has already been published that is actually to focus on the privacy preserving distributed average observers in distribution systems using, we integrate everything, we incorporate everything into the distributed average observers here. And another thing is about the holistic analysis of large-scale systems with large-scale DER integration, with grid forming inverters, and also in the context of hybrid AC and DC networks. We would like to highlight both the small signal stability as well as the large signal stability, and also mention the modular evaluation with definitely scalability guarantees. And for sure, for both applications of AC and DC configurations, as my colleague Dominic mentioned before, actually the hybrid AC and DC configurations could be a concern, and something of interest we can highlight here. So that is actually all of my presentation today. I really welcome any questions. Thank you so much for listening. Yep.
Okay, we'll go ahead and stop recording.